So what is this building for? Oh, this host computer science. Good evening, everyone, and a very warm welcome to all of you who are here for the Institute lecture. We have a very distinguished speaker amongst us, Professor Luiz DaSilva. He is currently the Executive Director of the Commonwealth Cyber Initiative and also the Bradley Professor of Cybersecurity, Virginia Tech. Professor DaSilva is an internationally recognized for his contributions to wireless communications and network research. He pioneered the application of game theory to wireless networks, and he is also known for his seminal work on cognitive networking and spectrum and networking sharing. Professor DaSilva has shared 2 books and published over 300 peer-reviewed articles. He is an IEEE Fellow for his contributions to cognitive networking and wireless resource management. He was also a Trinity College Dublin Fellow and an IEEE Communication Society Distinguished Lecturer. Without further ado, now I request Professor DaSilva to deliver his talk entitled Securing 5G and Future Generations of Network. Professor DaSilva. Thank you. So this. If it doesn't work, I can do it manually as well. All right, thank you. Thank you very much for the introduction, and thank you all for coming to this talk. It's really a great pleasure to be here. It's my 6th time in India, but the first time in this part of the country. Previously, I have been mostly to the south. And I'm really grateful for the invitation. Professor Shukla and I were colleagues many, many years ago when we had less gray hair, maybe more hair totally. But so it's also great to see him again. And I've been visiting C3i Hub all day today and been really impressed by the work that many of you have been doing in cybersecurity. So in Virginia Tech and in Virginia, my current role is as Executive Director of the Commonwealth Cyber Initiative. And the word Commonwealth here really means the Commonwealth of Virginia. So Virginia is a state in the US, but there are a few states in the US that are considered Commonwealth, and Virginia is one of them. So this was a group that was formed about 4 years ago, and it's funded by the government of Virginia with a mission of research, innovation, and workforce development. Is that working? No, okay. So I'll be moving around, so I might just, hopefully this is okay. So that's a map of Virginia. And Virginia Tech has 2 locations, one in the southwest, kind of at the bottom of the map, and one in the northern part of the state, right adjacent to Washington, D.C., and that's where I live, that's where I stay. And the Commonwealth Cyber Initiative was formed by the government of Virginia with a mission of research, innovation, and workforce development. So we're all researchers, we all work for some university. There are a total of 41 universities and colleges that are part of CCI. And Virginia Tech has the role of coordinating the activities of research, innovation, workforce development across these 41 universities. And those are the points that you're seeing on the map. And there are about 400 researchers working on this. So the topics that we cover basically span all of cybersecurity. Today I'm going to talk specifically about 5G and next-G security because wireless networks is actually my area. So a lot of the researchers in my group work on those problems. But if you take all of CCI, we span a lot of other topics. Some topics that I saw here being very well represented at the C3i, like securing the critical infrastructure, like the electric grid, for example, transportation, next generation of transports, and so on. I was going to show this video because it shows a little bit of a different side of to the work that we do. So the talk is going to be really technical about networks, and I wanted to show that there's some work that's actually quite different. And this is an example of that. So work that goes on with CCI that looks at using the arts to advance cybersecurity or to inform the public about cybersecurity. I'm going to show just a little bit of the video. The issue is that we can't get the audio, so I'm going to have to narrate some of the video, but I just wanted to show one or two of those projects. So this is a museum in Roanoke, Virginia, so in the southwest of Virginia, and we had, CCI had an exhibit at this museum of several projects related to cybersecurity, and those are projects done by artists. And there's one in particular that I wanted to show you. So this is some of the setup for the exhibit, but the one that I really wanted to show you is this one. Let me pause. So and this is a sound system that's created by this researcher. His name is Tanner of the Grove, and he does research on sound design. And what we did was we funded him on this project where he installed 30 loudspeakers on a frame. So you're totally enveloped by a frame. So you walk into the frame and there are loudspeakers all over, around you and on top of you. And what he does is he sonifies cyber attacks. So if you look at, if you visit a SOC, for example, Security Operations Center, you usually visualize cyber attacks. You have screens with graphical user interfaces, and then the cyber attack can be visualized on the screen. What he did was, instead of visualizing a cyber attack, he sonifies a cyber attack. So depending on the attack, you would hear it in different ways. So there would be different pitches, it would come from different places, depending on what kind of attack it is and what its provenance is. And so it started as essentially an arts installation, but now we are looking at how this could actually become a product. It could actually be incorporated into a center that is monitoring a system against cyber attacks. And there are a couple of other projects like these where, somewhat to our surprise, we started by looking at something that, what would inspire people or inform people about cybersecurity through the arts, but there is potential for innovation, commercialization of some of these projects. So if you're interested, the whole video is on YouTube, and I can point to that, or you can search CCI and you'll find the video with all of the narration. And it talks a little bit about the other projects that are part of this installation as well. Okay. So I'm not going to, let's move on. Okay, so ultimately what we are trying to do with CCI is to impact the Commonwealth of Virginia and the country and maybe even the world to some extent through research, innovation, and workforce development. So those are some of the numbers. So we do about, in the last 3 years, we did about $115 million in funded research, so research funded by either companies, by industry, or by the US government through various agencies like the Department of Defense, Department of Energy, the National Science Foundation, and others. We hired some consultants to look at what economic impact we've had in the first couple of years. So these numbers are about a year old. And they estimate that we created about 1,000 jobs through these activities. Okay, so this is CCI in a very short nutshell. And what I want to talk about today is specifically some work going on in 5G security. And that's an area that we have been investing in because it's an area of a lot of interest from the point of view of industry and government right now in the US, and where Virginia has particular research strengths. So Virginia Tech and some of the other universities that are part of CCI, like the University of Virginia, George Mason University, et cetera, they have real strengths in the area of wireless networks and networks in general and network security. So we've been investing in that. So I'll talk about some of those investments. But I actually want to start with a little bit of tutorial about 5G security. So, and then I want to move on to a discussion of what comes after 5G. So even though 5G is just beginning to be fully implemented depending on the country, we're already talking about 6G, and I want to talk about what that means, and in particular what that means for security. And then I'm going to shine a spotlight on some of the research that's done in my group. So we'll start broad about 5G, then more speculative about 6G, and then talking about my group specifically. The picture at the bottom is when we were setting up our NextG testbed. And what you see there are some of our students and postdocs actually putting up this infrastructure. So starting about talking about the evolution of 5G security. So as you may know, every 10 years or so, there's a new generation of networks. So starting way back in the 80s with 1G, so the first generation of networks, those are those large phones like a brick, fully analog and so on. And then about every 10 years since, there's a new generation. Now, what's really behind that is a number of different releases for standards that then get incorporated by vendors into product and then by operators into service. And then several releases are kind of packaged as a generation of networks. And we're currently in the 5th generation, already talking about the 6th generation. So I'm going to talk a little bit about 5G, specifically about security in 5G. And you could look at it as having two aspects. One is how to secure the access to the network. So how do you ensure that when you have a mobile or you have a user device connecting to the network, that connection is done in a secure way, that the device is talking to a real base station and not a fake base station that maybe some malicious actor has installed. How do you perform the handshake between the mobile device and the base station, and so on. So we'll talk a little bit about that. And then there's another aspect, which is the security of the communication. Once the communication is established, once the connection between the user and the base station is established, how do you ensure that the communication that follows is done in a secure manner? Okay, so for that, we'll need to get into a little bit of the architecture of the network to provide these security functions. And I want to compare it a little bit against what came before. So LTE is part of the 4th generation of networks. So what came before the current generation and how things have changed from 4G to 5G. It's a bit of an acronym soup, right? So when you talk about these standards, they use a ton of acronyms. So I've tried to put some of the acronyms on the slides. And so, but don't worry too much about these little blocks in the block diagram. I'm going to emphasize some that are of more importance. And I'm going to focus in particular on the authentication and key agreements. So how do you do the initial handshake between the network and the user device in a way that's secure on both sides, right? So that you can actually authenticate a user, make sure that the user is allowed to connect to the network, and also the user can be sure that the network is a real network. It's not a malicious actor posing as the network. So the authentication and key agreement is what provides this handshake and provides this mutual authentication between the user and the network, and the key exchange that then will protect the transfer of data over that connection. And what 5G does is it tries to address some of the vulnerabilities that were present in the fourth generation of networks. So in LTE, there are a few things that have been highlighted as specific vulnerabilities that 5G tries to remedy through a more robust mechanism for authentication and key agreement. And those are things like making sure that you protect the identity of the user. In 4G, sometimes the permanent identity of a user is transferred in clear text, so without encryption. And then that allows a malicious actor to actually track the user. So 5G tries to fix that. And the other thing is the authentication process itself in 4G occurs between the user and the visited network. And in 5G, this process is really done with the home network, and we'll show how that goes. Okay, so this is the timing diagram between the user, the home network, and the visited network. So the three entities that are of interest here. Let's see if I can get the pointer to work. Yeah. So we have three entities that I'm going to focus on. One is the user. This is the user equipment. So that's your mobile. This is the home network. So the network that actually has the credentials for that user, the network that's able to make sure that that's a user, that's the real user that has the appropriate key. I'm sorry, there's the slide set, I think, advances by itself. So it's going a bit faster than I'd like it to go. So there's the user on the left-hand side. On the right-hand side, the home network, and in between, the serving network. So I'm away from my home network. My home network somewhere in the US. But when I connect to the local network, this local network needs to go all the way to the home network to ensure that I can be authenticated. So the user equipment will contain in the SIM card, in the subscriber identity module, will contain some cryptographic information, so a key. And that key is shared with the home network, and we are going to call that key K sub I. The serving network doesn't have that key. So what is the process that happens in LTE? Well, the user tries to connect to the serving network. The serving network needs to then talk to the home network and say, well, I want to authenticate that user. The home network, which has the key that is shared with that user, then performs some cryptographic functions and generates what's called an authentication vector. And the authentication vector is going to contain a token. So an authentication token and an expected authentication response. And it's going to tell the serving network about that token and about the expected response. And the serving network then talks again to the UE, to the user equipment, provides that authentication token, and asks for a response from the UE, from the user. And then the UE uses its same shared key, K sub I, to validate the token, so make sure that that network is a real network, and then generates an authentication response. The serving network can compare the authentication response to the expected response. If they're the same, if they match, it's because the user was able to prove its identity, and now they can establish a secure exchange between the visited network and the user. So that is the way that it's done in LTE. Now, one thing that you notice here is that the only communication with the home network occurs in the beginning here. So the actual authentication is then done by the serving network. It's really doesn't involve the home network anymore. And the other thing is that some of this exchange of the identity of the user is done in clear text, or can be done in clear text, and therefore can be intercepted. So 5G tries to fix these two things. So fix the fact that the UE identity is being sent over the air in clear text, and that even though the home network is providing this authentication vector, it's really not making the final decision regarding authenticating the user. So it changes the whole process, and it defines new ways to identify the user. So it defines something like that's called the SUPI and something that's called the SUCI. So these are basically a permanent identifier, that's SUPI, which is never sent over the air in clear text, so it's always encrypted. And the SUCI is then the encrypted version of the SUPI, so which conceals some of the key information about the subscriber identity. And then the home network is able to resolve the SUCI into the SUPI. So it's a different way to identify the user in a way that none of the information about the SUPI actually needs to be transmitted unencrypted. And then it also defines some additional components in the security architecture, some of which I'm not going to talk about, but one thing of note here, which is different from previous generation, is that it also supports authentication through other networks that are not 3GPP networks, so things like Wi-Fi networks, for example. So it recognizes that typically you don't always connect through the cellular network that's defined by the 3GPP releases, and sometimes you have to connect through other networks like a Wi-Fi network, and it incorporates that into the authentication process. And then that same timing diagram that I showed before now is slightly different. And again, here there's the user on the left-hand side. Here there's the home network, and in between there's the serving network. And just to point out a couple of things, so the serving network now acts as a middleman between the user and the home network, but the actual authentication decision is done by the home network. So there is handshake all over. Before, there was only the initial handshake for the generation of the authentication vector. Now the handshake occurs throughout the entire process because the ultimate decision about authenticating the user occurs later by the home network itself. Then there are different modules within the home network that are responsible for that. So there is a module that performs authentication itself and uses a backend server for some of the cryptographic operations that it has to do. And then there's another module that actually de-anonymizes the user. So decrypts the SUCI into an SUPI. So all the communication through the visitor network only uses that SUCI, which does not contain the unencrypted information about the user identity. There are actually multiple ways in which this authentication is done, but the key things that I wanted to point out, which are very different, are the transmission of the identity over the air, and then the actual final decision about authentication being done by the home network. Two things that fix specific issues with 4G. Okay, so just a couple of comments. There's more to 5G security than that, but that is kind of one of the key ways in which 5G security is addressing vulnerabilities in 4G security. There are other functions related to things like slicing, for example, user plane integrity, non-3GPP support, and so on, which I won't go into in more detail, but generally 5G is viewed as a much more comprehensive security architecture than was present in previous generation. However, this is a continuous process, right? So even though we like to pretend that these generations are discrete, so there's 4G and then there's 5G that's completely different from 4G and so on. In reality, this is a process. There are releases that are issued every few years by the 3GPP, which is I keep talking about 3GPP and didn't really explain what it was, but it's the organization that essentially standardizes these generations of cellular communications. So the 3GPP issues releases every once in a while, and then several of these releases are considered under the umbrella of a generation. So for example, releases 15 through 18, which is where we are right now, is part of 5G. And at some point, some new release is considered part of 6G or whatever comes after that. So each new release is going to fix more and more of the identified vulnerabilities in the previous releases. So it's not, 5G is not finished. We're still, or the 3GPP is still releasing new releases. And now we are starting to talk about 6G. So what comes really after 5G? And to give you an idea of the timeline, so that's basically how long it takes for a new generation to emerge. It's basically a 10-year process almost, where the last few years have been focusing on the vision. So what are the ideas, the big ideas that are part of the next generation of networks that everyone is starting to call 6G. And then there's a phase, which is where we are roughly right now for the requirements. So starting to say, okay, what do we need from the network in terms of spectrum, in terms of general architecture to actually support this vision of the next generation. And then there's the standardization process where the 3GPP starts releasing new standards that are defined by that generation or for that generation. And then finally, there's products. So vendors will come out with products that then can be installed and deployed in real networks. So this is a long process. And we are somewhere along the way here in early days of this process. And in this phase, there is a new organization in North America called the IIT Alliance that's trying to consolidate ideas behind 6G from a North American point of view. So countries, of course, are part of large standardization bodies, but even before the standardization occurs, there's a lot of work in providing a vision and defining what that standard could actually accomplish. And that organization is trying to do that at this early phase in North America. It's mostly composed of companies, so the large companies that you're familiar with, so Ericsson and Nokia and maybe some of the operators and so on. And then universities can also take part of that. So Virginia Tech, for example, is part of the IIT Alliance. And that's one way in which we translate some of the research that we do into something that can actually influence the standards process and therefore influence the products down the line. Okay, so what do we expect to come towards 6G? Well, to some extent, I think what will come in 6G is a realization of things that were promised as part of 5G. So sometimes, the vision for one generation promises many things, and then in reality, that generation brings a subset of those things, and the next generation is actually going to come and complete that vision. So if you're familiar with 5G, or if you have read any papers about 5G, many times they show the vision for 5G as this rectangle with 3 vertices. So one talking about enhanced mobile broadband. So this just means much higher data rates supported in 5G. So that's one of the objectives stated for 5G. But there are 2 other objectives. So one is massive support of massive number of devices. So basically the Internet of Things. So lots and lots of devices connected to the network. And then a third one is what's called ultra-reliable low-latency communications. And that supports applications that are critical and therefore needs a very low delay for their control loops to work properly. And they need to be extremely reliable. Okay, so 5G really promised all 3 vertices. But most of the actual deployment is focusing on this vertex here. So enhanced mobile broadband. So that's what 5G right now is really providing, mostly. So higher data rates, so that you can support high quality video and other applications that require a lot of data. The other 2 vertices, the other 2 vertices are really not there yet. And there are different reasons that this is, these other types of services are not fully there. And part of it, I believe, is because the big players have not really figured out how to monetize these services, how they're going to actually charge for those services, where the market is, and there hasn't been enough incentive for them to really invest heavily, because it means large investments in the network to be able to provide those sorts of services. So what I would expect as these evolutions these generations evolve, well, I would expect to actually have full support for something like ultra reliability and low latency, because that's what's really going to change things, so be a big game changer in terms of the kind of applications that are supported by the cellular network. So cellular networks right now still support, by and large, best effort type of service. So, good service most of the time, but if the service fails, don't have coverage and so on, okay, it's annoying, but no one dies, right? But if you want the network to really support things like autonomous driving, for example, if the autonomous driving is really relying on the network, then if the network fails, then someone literally can die, right? So it's a different level of reliability that is needed. So that is what is largely believed to come. And for that to really come, there are a few big trends that are already present in today's networks in 5G, but are supposed to really be turbocharged into 6G. And I'm going to focus the rest of the discussion on these 2 big trends. So one is virtualization. So the virtualization of all functions in the network, which implies things like orchestration, softwareization, disaggregation. There are a lot of words that are used kind of, they all kind of relate to each other, having to do with more and more, you're able to virtualize different functions in the network and kind of dissociate them from the physical infrastructure. And the other is the incorporation of artificial intelligence in the network. So of course, the network already uses artificial intelligence. So even the mobiles, mobile will contain some artificial intelligence to help with things like association and so on. But what's expected is that this artificial intelligence will really be native in the network and will help drive the network, manage the network, control the network with less human intervention. And that's needed because as these networks become more and more complicated, sophisticated, it's very hard, even for experienced operators to actually operate the network. Okay, so these 2 things are there, and they create both challenges and opportunities in terms of security. So let's talk a little bit about some of those. So starting with virtualization. As I mentioned, this is already in 5G, and even before 5G, there was virtualization going on. So there are mobile virtual network operators, or MVNOs, for example, which operate fully on top of physical infrastructure that belongs to one of the large mobile network operators. So there's one level of virtualization. There's the virtualization of network functions that then can be performed in the cloud or in the fog, at the edge. So VNFs, or virtual network functions, are already there. Software-defined networking has been a reality for many years now, so that also brings virtualization. 5G brings the idea of network slicing, so you provide several network slices on top of a common physical infrastructure, so that's another form of virtualization. The use of white box hardware as opposed to function-specific hardware like routers and switches and so on. That's also already there. So these are trends that actually have been going on, and what we expect is for these trends to accelerate and evolve into new levels of virtualization. So this is a paper that we published a couple of years ago that looks at this new level of virtualization that is coming. So things like multiple radio access technologies supported over a common radio access network. So you have a physical network, but you could have different standards being supported by this same physical network, instead of having different physical networks for each radio access technology standard. So that's possible, and it would be a next level of virtualization. The orchestration of all these functions in a smart, intelligent way. The use of the mobile edge cloud, so more and more of the intelligence residing in the cloud at the edge, close to the end user. And network slicing. So these are some of the new things, in a way, that are starting to become reality. So what does that mean in terms of security? Well, there are some new risks that come with that. So if you imagine multiple virtual network functions that reside on the same hardware, and there are different types of attacks or vulnerabilities that you can envision. So, for example, data exfiltration between these functions. Oops. Oh, now it's working. Excellent. So you have these different functions. They all share the same physical hardware. So you can imagine one of these functions getting access to the data of another of these functions. So having an internal attack here between these network functions. You could imagine resource starvation, where one or more of these functions hogs all of the resources for itself, and thereby starving the other functions of resources. And side channel attacks. And then again, everything is residing on the same piece of hardware, not even performing these attacks over the network itself. Okay, but at the same time that there are risks, there are also opportunities. So now the same tools that are used for things like distributed denial of service mitigation now can be instantiated in a more dynamic way using these virtual network functions. So you could imagine the network dynamically provisioning these mitigation efforts and instantiating that in the different parts of the network. You could also use virtual network functions for things like intrusion detection, for example, or to instantiate a firewall or change the components or the behavior of a firewall and so on. So at the same time that you can imagine new threats, you can also think about how the same technology would prevent some of those attacks or mitigate some of those attacks. Another component that comes with virtualization is what is generally called orchestration. So now that all of the, or a lot of the functions in the network are virtualized and they're distributed, some of them are in the radio access network, some are in the core of the network. So how do you orchestrate the resources across all of these platforms to produce a service? So this is done by orchestrators, and you can even have a hierarchy of orchestrators. So you can have an orchestrator that just orchestrates things in the radio access network, another one that orchestrates resources in the core and function in the core, and then you can have a second level of orchestration, what's sometimes called a hyperstrator, which orchestrates the orchestrators. Okay, and so they do things like provisioning resources, they embed some intelligence, and it's a vital function if you're going to support these different types of services. So these are meant to represent slices over the network where each slice is dedicated to one particular type of service and really optimized for that service. And the orchestrator is taking care of what resources are dedicated to each of these slices. Okay, so now when we have an orchestrator which has all of this control of the network, then there are new risks that arise there because the orchestrator itself can be attacked. The orchestrator will often use artificial intelligence to do this provisioning across the network, and that part can be attacked as well. So you can imagine things like data poisoning or other attacks on the AI itself. You can also have opportunities. So each of these new technologies will have both. We'll have risks and we'll have opportunities. In this case, one opportunity is you can use the orchestrator as a way to mitigate attacks and detect attacks in a more dynamic way, a more intelligent way as well. And then another aspect that's related to virtualization is what's called disaggregation. So the fact that you can have, instead of a monolithic solution for the network, you can split the solution over different platforms with different vendors, and then all of this can be disaggregated, which has some advantages. It has some potential cost advantages, for example, by increasing the diversity of vendors that you rely on. But again, also comes with some risks. And the risks are often associated with supply chain type of attacks, because now as you disaggregate the network, you rely on a much more diverse supply chain. And of course, now you have to take care that there is trust. So you may have techniques like zero trust and security to ensure that all of the communication between these different components are happening in a trusted way. And there are opportunities. So today I heard a lot about some of the blockchain work that happens in C3i. So you could imagine using, for example, blockchain to actually make sure that the security of this disaggregated network is preserved. Okay, so I talked about virtualization. I mentioned that the second big trend that I wanted to discuss is the native use of artificial intelligence or native AI. Okay, the risks are those that anyone who is working on AI is now becoming familiar with, right? So there's a new generation of security attacks that focus on systems that rely on artificial intelligence. So things like poisoning attacks, so data injection in the training, data manipulation, logic corruption, model inversion. So you look at the model, try to infer information about the data used for the training. All of the attacks that any AI-based solution can be subject to, as you really embed AI into the network, now the network becomes subject to those same types of attacks. You can also use AI to combat some of these attacks. So we see a lot of the use of AI, and I'll talk about that later, for things like intrusion detection. And so where you try to even detect zero-day attacks that you haven't observed before, in an intelligent way using AI techniques. Then there are a class of security risks associated with privacy. And as we're focusing on the AI native aspect of the network, so what in these AI systems can potentially compromise user privacy? There's a lot of concern about IoT devices. So these are small devices that usually don't have a lot of capabilities in terms of processing or communication, therefore are more subject to attack. And by compromising these devices, you can compromise information about the users, right? So some of these devices will be monitoring people, monitoring health, monitoring your house. So a lot of private information that a bad actor could use against you. There are also opportunities. So there's a lot of work on edge-based learning to actually protect privacy. There's a lot of interest in research on homomorphic encryption. So homomorphic encryption allows you to perform operations in the data while still encrypted. So you don't have to decrypt the data first and then perform the operation. And so if you can do that, then of course you can preserve some of the content of the data itself and therefore the privacy. So those are some of the research areas related to privacy issues. And then finally, there's the possibility of attacks by AI on AI, right? So you can have a network that's actually controlled by artificial intelligence, and you could imagine a bad actor using artificial intelligence to attack the other artificial intelligence. And you're starting to get a bit into some science fiction here, where the human is completely out of the loop, and it's all these AI systems basically making war on each other. And then, of course, it becomes an arms race, right? So to see who can develop the more sophisticated answer to some of those vulnerabilities. So another area of research that's very hot right now is quantum information sciences. And quantum information sciences, both because there's an encryption worry related to the development of quantum computing. Right? So because if you have a quantum computer, you can break encryption that with today's technology would take centuries to break. You can probably break it in days or hours or whatever. So there's that aspect of quantum computing. But then, of course, there's a lot of interest in using quantum information science to accelerate artificial intelligence systems, to accelerate sensing systems, and so on. So you can imagine this arms race on AI in the network and AI trying to attack the network. Whoever gets the better access to computing power and data ends up having the advantage on that arms race. Okay, so those are some of the trends. None of this, I think, requires too much of a crystal ball, right? So these are things that we're already seeing develop at very high speeds. So there are aspects of AI, of course, that have just kind of made a big jump in terms of their capabilities, so ChatGPT and large language models and so on. So you could easily imagine that same leap in terms of technology development occurring in AI systems that are used to control large systems like networks. So that's something that's not too far ahead. And then virtualization also has been evolving for a long time and has been, it's pretty safe to say, okay, we'll continue to evolve and play a big role within the network. So we just try to anticipate these and work on some of the security issues and opportunities there. So I want to talk in the remaining time that I have about a couple of research projects. And the first one is about what's called Open Radio Access Network. And that's a topic that's very much in vogue in the US right now. So the idea that instead of relying on proprietary systems for networks, that we can develop open standards for interfaces between the different parts of the network and open up the supply chain. So right now, if you are an operator of a network, there are only a few vendors of network equipment that you can rely on. So they're large vendors, and they sell you the whole package. And once you buy from that vendor, then you basically stay with that vendor. So a little bit of audience participation. What are the big vendors of network equipment? Sorry? Nokia, Ericsson, Siemens, Juniper to some extent, yeah. Huawei. So yeah, so most of the big ones that will supply the entire equipment to an operator are going to be, Huawei has the largest market share worldwide, and then Ericsson and Nokia are next, with a little bit of Samsung and some of the others mentioned here. So they're very big. So between Huawei, Ericsson, and Nokia, they have almost the entire market. And once an operator buys from one of them, it stays with that system because they sell you the hardware, they sell you the software, it's proprietary and so on. So Open Radio Access Networks is trying to break that and allow the evolution of some open standards so that a new company could say, okay, I'm just going to supply the radio unit, or I'm just going to supply this particular unit, and you could build your network out of these different vendor components. And there are big economic interests involved in this, so this is not just a technical issue. There are some national security issues involved in this. If you think about, I mentioned Huawei, Ericsson, Nokia. None of these are based in the U.S. And so there's an issue that the U.S. is very interested in, this diversification of the supply chain and so on. So we have been working a lot with ORAN, with these open radio access networks. There's an organization called the Orion Alliance. That's the organization that basically supports the development of these standards. And what you're really doing is you're disaggregating. So you're allowing different vendors to supply parts of the network. And then you rely on these open interfaces. So the vendor can still have a proprietary solution for their part, as long as that piece that they provide talks to the rest of the network using these open interfaces. So it lowers the barrier to entry to new vendors, so diversifies the whole supply chain. So we have built in CCI a test bed. So these are some of the pictures from the test bed. So the test bed hangs from the ceiling. It contains 72 radios. So these little boxes are software-defined radios, so are the RF front end, the radio frequency front end to a software-defined radio, so that you can program the radio completely in software. And then the actual intelligence of the radio, the actual software sits in a server room. So there's a bank of servers that connects via fiber to these radios, and that's what really implements the software. So that's one of our big investments. This is a large test bed. These are not inexpensive radios. So some of these are tens of thousands of dollars, depending on the model. And each of these can play the part of a base station or can play the part of a user equipment. So they're very flexible because you can program whatever you want into the radio. And I won't go into the full architecture, but the architecture is all based on these open radio access network standards. And it's also fully open source. So we use, for every component, we use an open source implementation. And that's because we need to do research on this testbed. So our researchers need to be able to break things, need to be able to implement new things that have not been implemented by vendors yet, and so on. Okay, now with ORAN also comes some security issues. So they're both, again, opportunities and risks. So on the plus side, once you disaggregate the network, you can adapt a lot more. You don't have vendor lock-in, so you're not locked into one vendor. And there's more interest by these vendors since there's a bigger market and there's more competition in the market. There's more interest in them implementing, secure systems and so on. You can have cloud-native security advances like isolation of different features, automatic reconfiguration, and so on. And on the negative side is that now that you have all of these open interfaces, now each of these interfaces is also a surface for attack, right? So you can imagine an attack on each of these interfaces as opposed to everything being part of this monolithic closed system where you don't have access to the interfaces. Also, ORAN brings a lot of artificial intelligence and machine learning. So there's a whole component of ORAN that's based on artificial intelligence. And now artificial intelligence is much harder to verify. And therefore, you also have to worry about securing that. I'll get to your question, but since I'm running out of time, we may have to do it in the post time. Okay, so most of our research there has really been experimental. So we use the network. We now have a fully end-to-end ORAN compliant network based on open source systems. And now we can use the network to actually emulate an attack, or even create more than emulate, just create an attack on the network itself, since we have full control of the network. So we have a paper coming out in a conference now in June, where we report the results of a denial of service attack on an ORAN network. And basically, now that we have these open interfaces, you can imagine a malicious actor actually trying to flood the intelligence controller in the network with requests. And the network needs to deal with those requests at the same time that it deals with the requests from the legitimate nodes. So I will give you there's a bibliography at the end of the slides. So if you want to get the detail of this experiment, we're demonstrating that in the IEEE Infocom conference that's coming up now in May. Because I want to move on and show at least one more research project. So I had 4, but I'll skip the last 2 and leave it in the slide set if you're interested. But I do want to talk about one more because I think there's students and professionals here that are interested in artificial intelligence, and we've been using explainable artificial intelligence actually to provide additional security to the network. So that's a project that one of my current PhD students is doing for his final PhD dissertation. And it started because we wanted to open up this black box of the artificial intelligence that's being used for intrusion detection. So the real motivation was, okay, we all know that AI systems typically work as a black box, and they will give you a result, and the result can be very good, but you don't necessarily understand why it reached that particular conclusion. So Explainable AI tries to address that by providing explanations that are understandable by a human being. And many times those explanations come in the form of feature importances or indications of feature importance. So it will tell you, okay, these features have been key to reaching this decision. And there are different frameworks for that. There's something called the LIME framework. There's something called the SHEP framework and so on. So we started just applying to explainable AI to intrusion detection systems. But what we found out is that these explanations that come out of explainable AI can actually be used to refine the results of the intrusion detection system. And that's what we're doing now. So we take the explanations themselves, which, remember, the explanations are telling you this feature is more important than that feature, and that's why I reached such and such explanation. Now we can feed those explanations again into an intrusion detection system, and we find that by doing that, we can actually improve the ability of the system of detecting specifically new attacks that have not been seen before. So you detect attacks based on the training of this intrusion detection system. Then you put it through an explainable AI framework, and that will tell you which features helped you find those attacks. Now you feed those features back into the intrusion detection system, and it turns out that that improves your ability to detect attacks. So this is just a quick visualization. So the blue are legitimate traffic, and the red are attacks. And we're using some openly available data sets to train this. So once you put it through an intrusion detection system, it can differentiate between these two, but you can see that there are areas here that are very difficult to differentiate because they have kind of the same features, but it can be an attack, the red, or it can be legitimate traffic, the blue. Once you also use the explanations themselves into the system, now it looks like this. So a much more clear distinction between the instances of attack and the instances of legitimate traffic. So here's some data. So we can detect more than 89% of zero-day attacks by using the system. And you can increase the accuracy of the intrusion detection solution from 79% to 93%. So this is the work of one of my students, Peter Barnard, and we've been publishing in this area again. But so these are two examples, one more related to virtualization, disaggregation, and so on. The other more related to the use of AI, of actual research that's happening right now in this area. I'm going to skip the next two examples, which have to do with some new technologies, like reflective surfaces and millimeter waves, so new technologies that are increasingly being incorporated into 5G and beyond, so that we can wrap up with just a few minutes late. So just to summarize in 4 quick points. So first of all, 5G does address a lot of the vulnerabilities that were present in previous generations of networks. So it's overall more robust in terms of security, and in particular in terms of authentication and key agreement. But of course, every new technology that you bring into the network, that opens a new threat surface that can be explored. So it's a cat and mouse situation. So you're always trying to stay one step ahead. I focused on 2 key technologies or families of technologies that I think are particularly ripe for use in trying to mitigate attacks or prevent attacks, but also can generate their own attacks. One is virtualization, and the other is native AI. And then we always should have keep in mind these 2 sides of the coin. So yes, there are new threat surfaces opened by each of these new technologies. At the same time, these technologies offer new tools for us to fight security attacks. And I'll just stop here. So thank you very much. And you have some of the bibliography of the articles that I used here.
Thank you very much, Professor, for a wonderful talk. I think there were some questions.
There's a question here.
Yeah, go ahead. You can start from there.
Yep. It's not explicitly part of the Orion initiative. So the Orion initiative really focuses on these interfaces between the different components, and it defines where the intelligence should reside in the network. So let me show you a slide that I skipped. Yeah. So I won't go through the whole block diagram, but so these are interfaces that are defined by Orion. So there's A1, E2, etc. And then there are two places where Orion envisions intelligence being incorporated into the network, what they call the near real-time radio intelligence controller and the non-real-time radio intelligence controller. And as the word says, the near real-time one is for faster control loops, not quite real-time, but they reside closer to the application and so on. And the non-real-time is longer-term control loops. So the Orion Alliance only defines these components and the interfaces. How you're going to actually implement the components is up to the vendors. It could be a new company that says, okay, I provide a software version of this component that can run on a white box hardware. Or it could be a company that says, okay, I'll sell you this hardware with embedded intelligence or embedded software. So that's up to the companies. Every standardization tries to play this game where you standardize some things, but then the other things you leave for the market to innovate, right? So because then that's where, when you start your company, you're bringing your secret sauce and you're going to actually create something that's better than your competitors. So anyway, that's how it works.
Are there any other questions? Oh, yeah.
Yeah, so we didn't really expect to find this result. So this result was what happens sometimes in research, right? That you get surprised by, pleasantly surprised by a result. So we didn't set out to improve intrusion detection systems. We set out by saying, okay, for some of these systems rely on AI that control the network or try to protect the network, for them to really be widely deployed, there is the need to understand what they are doing, because there can be some resistance from the point of view of an operator, for example, to employ an AI tool that they don't understand why it's coming to a conclusion. It's just telling you, oh, okay, this is and this is an attack, but you have no idea why it achieved that. So our motivation for the work was to say, let's apply XAI to network systems. But what we ended up finding out is that the process of the explainable AI framework, something like the SHAP framework or the LIME framework, what they're really doing is they're trying to synthesize what are the features that really have led to the decision. And by doing that, they provide additional information. It's basically they're kind of giving you a little bit of imagine things are like in a fog, and then they're giving it a little bit more focus on the pieces of the data that allowed the detection of the intrusion. And so if you then take that, in addition to the training and the regular inputs, and provide that as an extra input to your system, we found out that that actually helps the system with the intrusion detection. And what we really believe is happening here is simply that the process that you're using for for the explanation, to arrive at an explanation, is synthesizing things about the data that are then more useful to know than just trying to look at all the data and make these decisions. So it was fortuitous in terms of finding out that this actually helped the system. So the student, Peter, it started out with one motivation, and then said, okay, but now why don't we apply this back into the intrusion detection itself? And it has improved the process. We're trying to determine how general this is, if that can be extended to some other applications, or if there's something about the intrusion detection and the intrusion of zero-day attacks in particular, which is a hard thing to do because you haven't trained for those attacks, because those attacks are not known a priori. So maybe it's helping just because of this very particular problem, or maybe there are some other problems that could benefit also from the explanation being fed into the decision process. We're trying to figure out how general that finding really is. Sorry, the denial of service attack?
Yeah. Hello.
Yes.
My question is related to DOS attack, denial of service attack.
Yep.
So this 5G and 6G does avoid this attack like fully, like 100%, or you mentioned about Orion, right?
Yeah.
So does it like 100% avoid this attack?
No, it doesn't 100% avoid the attack, and probably you'll never be able to do that. But so because what happens is you can have brute force denial of service attacks, have been around for a while now. But once you have a new technology, you could also have more intelligent denial of service attacks. So, for example, we were focusing on ORAN because as ORAN opens up these interfaces, now the interfaces become subject to denial of service attack, which is different from now, right? So now you don't have any access to the internal interfaces within the network. So you can have a denial of service attack between the user and the network, but not internally in the network. But as you open up the interfaces, now you can actually pose as a component of the network and produce a denial of service attack on another component. And then so now you have to protect against that new threat surface. So people working on cybersecurity have their jobs guaranteed for life, and because every new technology opens up a new problem, right? So you're always just trying to mitigate things. And people have a lot of creativity as well for evil, right? So creativity is not always for good. So people can come up with attacks that you have never considered before.
Sir, you told us that you are filtering packets based on 0-day and normal packets. How exactly you are doing that?
So, so one challenge in intrusion detection is zero-day attacks, right? Because intrusion detection systems usually work by training according to data that you have on previous attacks and signatures that come with those attacks. So it identifies that a particular kind of attack has a particular signature in terms of how the packets arrive, or and so on and so forth. The problem with zero-day attacks, of course, you cannot train for them because you have no data. So there is no way to do really supervised learning that's specific to zero-day attacks. So what we have found out is, well, one way that intrusion detection attacks sometimes work is they do multi-tier classification, where they can say, this is an attack that I have seen before based on my training. This looks like legitimate traffic because it has a signature that is similar to legitimate traffic that I've been trained for. And this is a question mark. This could be a zero-day attack because it doesn't quite look, the signature doesn't quite look like legitimate traffic, doesn't quite look like an attack that I've seen before. So there are some systems that already do that. So, and of course, the level of confidence in this middle tier is not as high as the other two. And then one thing that we saw is we can increase that confidence by using these explanations as part of the decision process. So we don't solve the problem completely, but instead of having a low confidence, it's just saying, okay, this traffic has signature that I just can't really tell whether it's an attack or not. I have a little bit more confidence that it is an attack, even though I haven't seen it before. Because maybe it has some features that are common to larger classes of attack.
Any more questions for the speaker? If there are none, I would like to take this opportunity to thank the speaker again. A round of applause, please.
Thank you all very much. Thanks for your time today.
We have a small memento for the speaker. May I
Oh.
request Professor Manindra Agarwal to do the honors?
Thank you very much. So this is going to be in my office in Virginia next week. So thank you. And thanks again for staying, so long. I'm sorry that I went a little bit over time today.
Thank you very much for a wonderful talk, and thank you all for joining us. Have a nice evening.